what we are going to do in this class, and again, this is going to be very exciting because it will cover many different aspects, is we are going to design a cube satellite. And I'm going to talk about what a cube satellite is, basically a small satellite that is able to communicate both with Earth and communicate with neighboring satellites. In other words, it's going to have two antennas. One is for Earth communication. The other one is for communication with other satellites. And basically from now on until the delivery of that project, which again, I'll give you a specific date once I go and look at it, we will go over a series of steps. So first, if we want to have a satellite designed with antennas on it, we want to make sure the antennas are well operating and whatnot, and the structural design is good and whatnot. We work backwards and we basically go step by step. So again, just to recap, we're going to quickly go over some of the things we learned from last class, again, to make sure we're on the same page. We're going to look more now into the patch antenna, the directional antenna, because last time we did the omnidirectional antenna. We're going to continue our real-world engineering assessment, so I'm going to need you to stay focused and do some work with me over here. And then finally, I already did that part, go over the project, the big picture, and now we're going to actually break it down into increments and see where to start. So, quick recap. Again, this is an extremely important slide. We're dealing with antennas which stem from electromagnetics. And I'm going to go over these four Maxwell's equations because they are very important. Gauss's law says you can only have an electric field if you have a charge. And that's why an antenna radiates, because charges are usually flowing through the surface, through the metal. And based on that, the charges exert an electric field. Now, the electric field usually has a certain range and just kind of stays there, but it doesn't travel like a wave. In order to travel like a wave, you need a changing electric field, which means you need your charge to actually move back and forth. So this is actually what, for example, Maxwell's law here is saying is that, okay, once you have a current or you have a changing electric field where there is charge, but it's not just sitting there, it's actually moving, that movement of the charge causes a changing magnetic field. And based on that changing magnetic field, from here, we know that that causes a changing electric field. And this dance goes on forever. And what you have is an electromagnetic wave, which is what an antenna actually propagates in space. So to be clear, if you want to use an antenna, you want to make sure you're feeding your antenna with some type of current that's going to propagate into the air. In other words, that current has to be changing electric fields and changing magnetic fields. Now, if you're feeding it DC current, if you're feeding a wire DC current, let's say the wire is the antenna, are you going to have an electromagnetic wave? Can someone tell me? Yeah. Well, first of all, what is DC current? Direct current. What is that? Direct current is basically charges flowing in a single direction uniformly at the same rate. Okay. So it's basically what your phone uses to charge. Like if you plug your iPhone into the wall, that basically is DC current, because it's basically just carrying charges in one direction. It's pretty boring. Now, if you were knowing what we know about Maxwell's equations, if we were to take that kind of current where, again, let's say this is my antenna and I'm feeding it this current, which is only flowing in one direction, based on what we know from Maxwell's equations, am I going to have an electromagnetic wave? So what happens is if I'm feeding it direct current, basically the electric field is changing linearly. Okay, so it's changing at a constant rate, basically. And if I were to take Maxwell's equation and say, okay, based on this change in the electric field, I'm going to take the derivative of that to get the magnetic field. The magnetic field is going to be constant. So if you have a linear function like y equals mx plus b, and you take its derivative, you'll just get a constant. Now that constant, if you were to take the derivative of that, you're going to get 0. So you're not going to induce a further on electric field. So the key idea here is that if you want to have an antenna operating, you need to feed it alternating current. You cannot feed it direct current. And again, because what is alternating current? Alternating current means instead of me just feeding the charges like this in a boring uniform direction, my charges actually do this. They go back and forth, back and forth. So they move, decelerate, stop, accelerate, move faster, stop, and so on. So this acceleration and deceleration that's happening constantly, what that's basically doing is it's changing the electric field constantly, which therefore changes the magnetic field constantly, which therefore induces an electric field constantly. Okay, so this is very important when you want to understand antennas, and this is why Maxwell's equations, especially these two guys, are very important, because they tell you that, hey, if you want to have, at least in the context of wave, if you want to have a changing magnetic field, your electric field better be changing. And if you want to change an electric field, your magnetic field better be changing. And hence, that's exactly what happens in a way. Unlike what we see here in Gauss's law, where this is good enough for DC current, because this is basically telling you that, okay, if you have a charge that exists, it's going to have electricity. It's going to have energy. And that's good enough for the purpose of charging, for example. Are we clear on that? Okay, cool. Is anyone confused? This is very important. So if you have like stupid question or still not sure, please, now is the time to ask. Okay, cool. All right. So again, going back on that, we transform into the idea of antennas, where these antennas now all of a sudden take your alternating current and they're able to propagate it in the air. Or likewise, they're able to receive propagating waves from the air and capture it into current. So what we covered last time is that there's two types of antennas. You could have them directional or fairly omnidirectional, as in like they transmit everywhere. And what we did last time is we went over how you design something like that. We chose a monopole antenna, and we were able to relate the frequency, and therefore the wavelength, to the length of the antenna, okay, which is pretty straightforward stuff. Now, let's say that I want to do something more fancier than that, and I want to actually be able to transmit in a single direction. And we're going to talk about that for a little bit. But before we jump into that, one application that's very important for having directional antennas and omnidirectional antennas is satellites, okay? So satellites are extremely important because, well, now we use them for communication, but we also use them for weather monitoring. We use them for all these, we use it for GPS, like if you're ever using Google Maps or Apple Maps, they're basically constantly communicating to satellites. So this is something that's very important, but let's just define it real quick. What is a satellite? Satellite is basically just anything that revolves around something else. So for example, the moon is a satellite. It's a natural satellite because it's revolving around the Earth. And likewise, the Earth is a satellite because it is revolving around the sun, and so on. For example, if something is revolving around an object, we call that a satellite. Obviously, in this case, we're talking about satellites that we build. So they're not natural satellites, they're artificial satellites. And usually they can be pretty big. They can be like massive, size of your house, or they can be small. And again, this is just showing you, for example, how a satellite orbits, is that it just goes around something, okay? Now, obviously, we know from mechanics that because the Earth has a mass and the satellite has mass, they are going to attract each other. So actually, this rotation is not going on just like that. What's actually happening is that each time the satellite gets a little closer to the Earth, a little closer to the Earth, and as the satellite gets closer and closer, it starts accelerating faster because the gravitational pull becomes stronger. Now, lately, and when I say lately, I'd say probably like in the last 15, 20 years, and especially like in the last 5 years, there has been something very exciting in that we were able to advance electronics, batteries, solar panels, and everything in such a like mechanical technology in general, manufacturing, such that we're able to take these satellites and make them much smaller. And this is really cool because we can make them a lot cheaper, and we can now start experimenting with things. So this is what a cube satellite is. It is a cube. It's a satellite that's basically like a cube. So this here, believe it or not, this thing actually goes to space, and using this antenna, for example, this is an omnidirectional antenna. In this case, they use a tape measure, which goes again to show you that if you have any piece of metal, as long as it's the right length, it will act as an antenna. That's very cool. And then likewise, they have something over here. Not sure if that's like a patch antenna, for example. This is probably a patch antenna. So this is like a patch that you slap and it's going directionally. We're going to talk about that. You have like some sort of camera over here. And likewise here, you have like a camera. You have like, in this case, these solar panels, they deploy. So they're stacked on top of each other. And then suddenly they like deploy. Now that way you have more exposure. You're able to capture more solar energy, which is very cool. So why are we talking about CubeSats? Because again, if you're going to learn about if you were to pick one application where ANSYS as a software and simulations are very relevant, it is satellites. Because one, you have to simulate the antennas. Two, you have to simulate how it's going to behave when it's going to vibrate in the rocket, once it's released, once it deorbits. These are all simulations related. Also, once you launch a satellite into space, you can't really get it back. You can't go up there and fix it. So this is another example of why simulations are extremely important, because you want to make sure you have covered every single aspect and you expect what it's going to behave like, such that once it is in space, it behaves perfectly as if you have imagined. Okay. Now, obviously, there are sometimes things that go wrong. For example, a Hubble Space Telescope had issues. They had to send people to fix it. Sometimes some satellites, they just have some problems with deployment. For example, the solar panel, there could be a mechanical problem with the deployment, it just does not deploy. Sometimes the rocket explodes on the way to orbit. Obviously, now that's not as much of a problem. Rocket technology has gotten a lot better. But you cannot control everything, but you can use simulations such that, to the best of your ability, reduce the likelihood of something going wrong. Okay.
So,
all right.
are the CubeSats like the satellites that are like the Starlink and like the Google are like sending all those a bunch of satellites? So is that a CubeSat?
Yeah, that's an excellent question. And yes, that's exactly what they're doing. So for example, SpaceX, Blue Origin, what they are trying to, especially SpaceX with their Starlink constellation, they're basically taking CubeSats that are around the size of the one on the left side. So they're like, I think they're 3U CubeSats. We'll talk about what 3U means. And that's exactly what they're doing, is they're sending so many of them. And basically their idea is that if you have way too many, instead of using a few large ones, these few can talk to each other, and then they can coordinate, and they can provide space-based internet, for example, in the case of Starlink. If you're curious about Starlink, I actually, or this idea of space-based internet, I actually wrote a paper on this topic, and I published it sometime in April. So I can put the link to this. So what I over here, I actually won Best Paper Award. It was a really good paper. So I'm going to put a link for that. If you're curious about Starlink, or basically these CubeSat constellations in terms of how they are designed and how they're able to provide internet coverage worldwide, I highly recommend you read this when you get the chance. Okay, I'll send it out in the end. Okay, cool. So, all right, now back to, no, that's not it. Please, yes, that's the one. Okay, well, no, that's not the one. All right, that's the one. All right, cool. So now that we have that figured out, okay, so now we know what CubeSats are. They're basically small satellites, again, very cheap, very cost effective. We can send too many of them. SpaceX, I think they plan on sending 20,000 of them. That's just bizarre. So now, why are directional antennas relevant? So again, last time we spoke about omnidirectional antennas. In this case, we're going to talk more specifically about directional antennas. And directional antennas is just like what it sounds. It's sending energy directionally in a certain direction. So for example, if you have like a radar, or like, again, a radar is nothing but like a transmitter and receiver. Same thing essentially as a radio, or a radar will use an antenna. So if this radar antenna is transmitting in this direction, it's doing that directionally. And likewise, for example, if we have two directional devices looking at each other, it is important that they point at each other. This is basically showing the electromagnetic energy radiating. This is the main lobe. This is basically what this blue thing is. And if you have two things that are both directional, you want to make sure they're pointing. So we're going to talk about how that actually impacts satellites. This is actually one of the biggest challenges for SpaceX Starlink, is that because they are trying to use lasers, which have very narrow directional beams, is you have to get the thing to point perfectly and exactly at each other. So we're going to talk about that. But just very simply, can someone tell me why you would use a directional antenna over an omnidirectional antenna? Because if I have an omnidirectional antenna, I can just send my energy everywhere, and it doesn't matter if you're here or here or here, you're always going to receive it. So yep, go ahead.
Are they more like energy efficient?
Yes, exactly. So instead of me sending my energy everywhere and having my receiver capture only some of it, why don't I just focus all my energy where I actually want it to go? So this is going to be the most important application of directional antennas. Now, especially in space, because you have your satellites usually really far away from each other. For example, if I have my phone right here and I have my like Wi-Fi router somewhere in the living room, we're like 10 meters apart, if even. So my phone is omnidirectional, my Wi-Fi router is omnidirectional. They both are more than comfortable transmitting energy everywhere because I'm close enough where it doesn't matter. Now, directionality is basically something you think about when you have range, versus in satellites, if you have satellite that is like 200 kilometers apart with the other one, you want to use something directional. Because the reason I included this second figure here, what I want you to gain from it is that as the distance gets larger, the energy spreads out more and more, and there's less to detect for your receiver. For example, if you have this guy right here, which is standing close enough to the radar, it's still, let's say this is the size of the receiving antenna. They're both the same size. This guy is capturing most of the energy, so he's getting very strong signal. But by the time you move a little further away, the beam keeps diverging, and now you're capturing even less of the energy. Now imagine if you have a guy that's over here, and then really far away. So even directional antennas, as the distance goes on, the beam will start diverging, and you're only going to capture only a little bit of the energy. Okay, so this is why distance is such a huge thing for satellites. Okay. So does anyone have any questions so far on directional antennas? Yeah. So this is again relevant because not only is your energy diverging, which means you're capturing less of the signal, but also if you're standing far away, you may be way too far such that your energy has diverged enough where it has become so weak that you don't detect anything. Okay. So for example, if you picture and that's actually, for example, what this like the sun is an omnidirectional antenna. So if you think about the sun is transmitting everything omnidirectionally, 360 degrees. Okay. So naturally, we on Earth, once we're facing the sun, the whole sky usually lights up because we're basically capturing the entirety of that beam. But as the Earth rotates and basically we're not pointing in the direction of where the sun is, that beam kind of starts diverging because we're no longer looking at it again. And likewise, if you have someone that's like in a faraway galaxy, you're not really going to see the sun as bright as we do because you have gone way too far, so far away, such that the energy that's coming from the sun is so weak that it's far weaker than like whatever objects are close to you. Does that make sense?
Yeah, that sun comparison made a lot of sense. Thank you.
Yeah. So and likewise for like light bulbs also, like, so light bulbs are omnidirectional antennas. They're basically sending light 350 or 360 degrees everywhere. But if you want something that is focused, you can use a laser, which you can actually reach the moon with. Because again, you're focusing the energy so much. But now that same laser, if you were to point it at like Pluto or like a nearby galaxy, by the time it reaches there, it's going to diverge and they're not going to see anything. Okay. All right. So following up on what we did last class, so we designed an omnidirectional antenna, again, because we did not care about directionality. We picked a frequency, which we converted into wavelength, which we converted into an actual antenna length. We didn't really care about the bandwidth, and we just wanted to make sure it's mechanically robust, nothing too fancy. Now, in this case, if we were to design a patch antenna for a CubeSat, again, let's say we want the CubeSat to talk directionally to another one. So we mentioned that this is like an omnidirectional antenna where this is the directional one. So this is going to send a beam that goes upward. It's not going to be too narrow because patch antennas are usually not very narrow. They're not very narrow. But yeah, so if I were to go through that exercise, first is frequency. Let's say we're going to use, again, the same frequency. So let's say it's, again, 2.4 gigahertz. And we're just going to use that because that's a kind of generic frequency to use. So based on this frequency, that we also are going to use the same wavelength, I basically want to figure out what's going to be the length of my antenna. But in this case, it's not just a wire. So it's not just length. It's both length and width, right? So what is the dimensions of the antenna? Now, will the dimensions depend entirely on frequency, or will they also depend on bandwidth? Let's say my bandwidth I'm interested in is 50 megahertz. Okay. So how does that affect my actual design? And as far as constraints, again, we're going to not place anything. For gain, let's say we want it to be nothing too fancy, like let's say 3 dBi. Now what 3 dBi means is it basically takes your power and doubles it. Okay. So instead of sending power everywhere, it kind of shrinks it down such that you're sending it in one direction. So the gain, basically the larger this number is, the more directional your antenna becomes. Okay. Now, are you guys familiar with decibels as a unit? Okay, cool. So does anyone know why we use decibels when we talk about antenna gain? As in the amount of energy you add to your beam just from geometry alone? Yeah, exactly, by a square. So that's exactly right. So as your energy starts traveling, you lose energy due to something called the square inverse law, or inverse square law. So it looks something like this. Now, once you have something that looks like this, and you can see that things are actually decaying at a very large rate, all of a sudden your distances using linear numbers does not make sense because you're losing magnitudes. So I'll give you an example. My phone right here is transmitting at about 100 milliwatts. Okay, so that's about 0.1 watts, which is about 10 to the minus 1. Okay, so if I were to, by the time this is actually transmitting 360 degrees omnidirectionally, by the time it reaches the nearby cell tower, for example, let's say it's really far away, it could be all the way down to like 10 to the minus 9 watts, okay, nanowatts, okay? So because your signal is decaying at a very large rate, as in you're going down 8 magnitudes, that means 8 zeros next to the number that you started with, it makes sense to use decibels, okay? So whenever you are using decibels, you are generally dealing with things that either get large very quickly or get small very quickly, okay? So in this case, with antennas, I could, in theory, instead of saying 3 dBi, I want an antenna that basically doubles your power, so it has a 2x factor. But let's say I want an antenna with like, I don't know, 50 dBi gain, okay? What that basically means is you're taking the power you initially started with and you're adding 5 zeros next to it. That's a lot of power. Hence, it's much easier to use 50 than 10,000, okay? So again, don't get too confused by decibels. They are basically just there to help you make the numbers smaller. So it's just a lazy way for humans to not type out large numbers, okay? So lastly, usually when dealing with decibels, it's usually dB. That's the unit for decibels. However, in this case, I added an I. It's dBi. Does anyone know what this I stands for? I don't know if anyone has looked at this before. No? Okay. So what this I stands for is for isotropic. And this is basically what basically this means is I want this to be 3 decibels more than an isotropic antenna, which is one that transmits 360 degrees. Okay. So this is also a really good way to think about decibels, is that decibels are all about relationships. So how much is something getting larger or smaller in comparison to something else? In this case, this something else is this I, which is the isotropic or omnidirectional, same thing. Okay. So now, if I were to tell you, okay, design a patch antenna for this given frequency, what should be your first step in the actual design process? Again, no wrong answers, just think out loud.
You need to look up what the equivalent for like the antenna length would be for a patch antenna for dimensions for that.
Yeah, exactly. So you want to figure out the dimensions of the antenna, right? So then let's say we can go on Google and we can say patch antenna design. Well, we could be lazy and use a calculator. Let's actually see. So there are calculators online where you give it, well, this is basically the substrate you're using, the frequency, and then it will tell you, okay, so these are the 2 equations. This is what I was looking for. So we have length and we have width, because we are using a rectangle. I'm going to zoom in on this because I want you to see what this looks like. So if this is my patch again is just a square, basically what's happening is I have a square. Okay, so I have a length and a width. Now these lengths and widths will have something to do with the frequency, but also with the bandwidth. Okay, so we're going to figure out which one's responsible for the bandwidth, which one's responsible for the frequency. Now, what we see is that there's also a ground that is connected to through this substrate. And in between, there's a dielectric, okay? So basically what's happening is the energy is flowing between this ground and this patch and then basically radiating out into the space. So the part that is most interesting to us is the length and the width of the patch, right? Because this ground, really, you could make it as large as you want or as small as you want. If you make it really, really large, that's like usually the ideal case. But usually if it's like, as long as it's big enough, it's not really going to influence what you're doing too much. So now let's go back to the equations and see how we decode some equations. Now, if you look at this initially, it looks kind of terrifying. But basically, so this is FO, which I'm guessing is the frequency of operation. So let's say the width has to do with the frequency, okay, and then the length is also dependent on that as well. So let's say we don't know what this actually means. Like, let's say we're looking at well, this is just looking at some comparison. So upon initial inspection, we know that, okay, there are some equations for length and width, but let's say you don't understand. I'll be honest, this is something I do very frequently, is if I click on a link and things don't make sense or like are not very well explained, I usually click off and go look somewhere else. So for example, if we go and look somewhere else, let's say if, again, this is a calculator, we see that, okay, then we have the width and the length. Okay, and they say, okay, you have to do things in a certain order. You have to first calculate the width, and then based on that, you can calculate your length. And we look at the variables involved, and here things are very well defined. So again, yeah, this is the resonant frequency. Now, does anyone know what resonant frequency means? Resonant frequency just means the central frequency of operation. So if I'm at 2.4 gigahertz, basically that's my resonant frequency. And based on my bandwidth, let's say my bandwidth is 20 megahertz, I'm going from 2.3 to 2.5, okay? So the bandwidth is basically the window of how many frequencies you're using, but the resonant frequency is the central one, and that's the one that's the most important. Okay, so we know that we can design the width, we can design the length. Okay, and then, so what is this? So we know that C, for example, is the speed of light. Okay, we know that variable. The relative permittivity of the dielectric substrate. Now, what is this going to depend on? Does anyone know? So if you remember from the picture in the last one, we saw this guy right here, the dielectric. Okay, so what is this value going to depend on? How are we gonna grab this value? Does anyone know? What does it depend on? Why would the permittivity of a substrate change from one to the other? What is the main thing we're looking at?
Is it the material?
Is the material, exactly. So if I'm using like plastic or wood, or if I'm using air, all these things will have different dielectric constants, okay? And that will basically impact how fast or how slow your waves are jumping back and forth between that ground plane and the patch. Now remember, because so things in the air travel at the speed of light, but as soon as you enter a material, you start penetrating a material, that material will slow down your wave and it will make it behave in some sort of way. So this is also important in terms of our design. Now, lastly, okay, so we know that, so again, let's isolate the variables. Like when we're looking at the width, so we have the speed of light, got it, frequency, got it, and then basically this effective dielectric constant, or the permittivity, I guess, in this case, relative permittivity of the dielectric substrate will depend on the material we choose, okay? So again, let's assume we use, I don't know, like a foam of some sort, then we can come up with the width very frequently. Then based on that, we will need to calculate this effective dielectric constant, and based on that, we will use it to solve for the effective length. So basically what this equations are telling you is the length and the width based on your desired frequency, right? So you have the frequency in here, and then we have these two other variables which will depend on the material of use, right? So if we go back to, okay, so if we go back to here, we have the frequency taken care of. So let's say we have our length and our width, but what about the bandwidth? How do we actually figure out the bandwidth, right? That's one requirement. So then naturally what I would do, for example, is like what determines bandwidth of patch antenna, okay? Okay, so if we go and look at it, okay, let's go on antennatheory.com. They probably explain how the bandwidth is related. So here again, they're telling us about the length, the width, and again, this is basically what we covered with the ground plane. And then here, if I go Control F and I look for bandwidth, which is what I'm interested in. So it says the width of the microstrip antenna controls the input impedance. Larger widths can also increase the bandwidth. Okay, bam. So this is a new piece of information that I did not know, is that, so the length and width will determine the frequency, but the width actually has to do with the bandwidth. So how do I relate the bandwidth to the actual antenna? So one way you could do that is you can actually go and try to figure out theoretically what happens. In other words, try to figure out like the equation that relates bandwidth to the actual antenna dimensions. Or if you want to be lazy, like a really good engineer usually is, you actually go and simulate the thing on ANSYS, and you see how your bandwidth is, and you kind of play around until things are figured out. Okay. So again, as an engineer, so I teach this class from like a hardcore engineering perspective, which like engineering to me is like tinkering, playing around, figuring things out on the go, Googling things until you have no idea what's going on, and then something magically pops up. Versus the other way of approaching problems is to go entirely from theory and go try to figure everything theoretically and then simulate it perfectly in the simulation environment. Now, to me, this makes absolutely no sense, because a simulation tool for me is a learning tool. For example, I don't know about you, but for me, it's much more efficient for me to learn if I click something, run, and see what happens, and I try to like reverse engineer the process. Okay, sometimes if you get stuck in more of the advanced theorems, like let's say with electromagnetics, you have no idea why a certain antenna behaves a certain way and whatnot. Or for example, if you were to take this and plot it, you plug it in into ANSYS, and then change something in the width and simulate it, and then change it again, simulate it, see if it's increasing and decreasing, and then that way you can figure out exactly what to do. So the reason I say that is because, again, going back to this idea of, let's picture you are at a full-time job, or you're at an internship and you have an assignment and you don't really know what to do. There's always going to be my preferred approach, and this I guess depends like a lot on personality, is I first take a look at the equations and try to make sense of what's going on, kind of like what I'm doing here, just do a lot of Googling. And then when I reach a point where I isolate a variable, where, for example, I know that the width will determine the bandwidth, I go search for an equation that directly correlates them. And if I'm not able to find that quickly, I'm just going to go simulate the thing and play around with the bandwidth until I see, okay, what exactly is going on. And then if I want something that's exact, then I can go back and basically deduce that knowledge from the equations. Does that make sense? So again, this idea of how you approach the problem is very important. So like, let's say that for now, bandwidth is megahertz. We know this depends on width, but not sure yet. And basically, we're going to use the simulation as a way to actually test for that. Okay. Now, again, as far as constraints, mechanically robust, ideally, you'd want me, for example, to give you a specific material, a specific substrate for the dielectric, but generally, I do not. Let's say I do not care, then you would make sure you use something that is highly conductive and strong for the metal, and then something that's also strong and highly dielectric for the dielectric. Okay. So does anyone have any questions so far? Okay, cool. So now we have about like 5 minutes, 6 minutes left. So what I was going to do is I was going to basically open up Workbench and basically give you the main idea of designing the structure of the CubeSat. So again, what I want you to do, and I'm going to post this on Canvas also, just as a reminder, by next class, I want you to come up with a list of requirements for this whole project. So first thing you notice is I use a 3U CubeSat. Okay, so this is clearly like a CubeSat designation of some sort. Your job is to figure out what this means. Hint, it has to do with the size. And then basically come up with a list of requirement, or basically list of questions on what you think is important and I need to provide you with. Okay, do that. And then by next class, what we're going to do in person is we're going to actually sit together and try to design the structure of the satellite. Okay. So again, by next class, it's very important you come up with a list of requirements, especially if it's like mechanical requirements for the actual CubeSat. Again, this is a 3U CubeSat. So I want you to keep that in mind, what that means. And then based on that, based on the two antennas we talked about here, which we still have not simulated, we have a rough idea of what's going on. I want you to tell me if you need more requirements for that, or you think this is basically good enough for you to get started. And then in class, we're going to design the structure. And then following from there, once we have the structure, we're going to actually go on, take a different approach and use the electronic desktop, okay, and actually do some antenna simulations, okay? So in the next few weeks, we will do some kind of jumping back and forth, but this is, again, very important for me because as far as learning, I call this like calibration, is that you, like, let's say here we're working on a mechanical problem and an electromagnetic problem, and they eventually both converge into what we want to achieve. To me, something is very useful is if they depend on each other, for example, the size of the antenna depends on the mechanical structure, it's very important that you kind of go back and forth where you're figuring out your mechanical design, then you're looking at your antenna and saying, okay, what you're trying to do with it, maybe simulate it, then go back to see how that fits into the mechanical design. When you are able to comfortably switch back and forth between that, the whole system, the CubeSat, is in your mind the whole time, and basically you don't diverge away and end up wasting a lot of your time on something that is not relevant to the project. Does that make sense? Okay. All right. So we don't really have much time to start the structural design. Wow, these classes go by way too fast. This is basically half of what I wanted to cover today. But okay. So next class, we will design the satellite structure. And I want you to come in with dimensions ready. Okay. So again, requirements for the satellite structure and more requirements for the antennas if needed. Okay. Does anyone have questions?